Okay, so today's our chance to see how poll everywhere works, right? Okay, yeah. So based on your feedback, poll number one last Friday, right? So I've received a lot of interesting suggestions. Actually, some of those programs which you guys suggested I never heard of, right? So that's pretty amazing, right? But in the end, like the combination of features and the level of integration, which is almost none, but there is a Python script, right? Which will allow us to extract activities from poll everywhere, well, kind of pushes us to use poll everywhere. The main disadvantage is that it doesn't support markdown, so you cannot really, if you want to ask a programming question, you cannot really. So because what poll everywhere allows you to do is just put a regular sentence in a question, and that's about it. Or you have to go with a picture, like one or the other. So we'll see it later today. But anyway, so let's try it. So a couple of announcements, right? So first, homework number one is out, right? I asked you in that homework to build shell. It's a lengthy kind of page which tells you about how to use GDB, how to build shell. So I recommend you to start early. We gave you 2 weeks. I believe it's sufficient time, right? So, and it requires a lot, like some minor setup. So you have to set up your Kate account or figure out how the compiler toolchain will work on your own machine, right? Then you have to understand how shell is working, stuff like that. I also give you a couple of hints, right? So in the top of it, I said, okay, this is based on this and this blog post. So you can look, but maybe try not to look. But what I argue you can look is implementation of a shell inside the x86 operating system. And I provide a link, right? So, and mainly, again, if you're completely confused about how to invoke those functions, like fork, exec, how to combine them in a recursive manner, so go ahead and try to read the source code. But again, the code which you submit should be your own, right? So even if you looked at something and refactor something, just make sure that in the end you submit your own code. And again, like there is a sub part in that homework which requires you to figure out how to use GDB. And again, you can there is a certain level of integration of with Microsoft Visual Studio, right? So which seems to be one of the best code editors. Like there is no ideal code editor, but that's a decent one. So you can try to use it, right? And if you say, okay, we feel that it's so cool, it works so nicely, I can go with it as well. Okay, so that's announcement number one. Second is like my office hours. Since I said I cannot do that on Tuesday, I can do them today. So after the lecture at 11, let's say. So come see me in my office if you need anything, and I will be next week. I will be there on Tuesday, right, for you to help with the homework. And also TA's office hours are there too. And like finally number three, which you kind of got it already, like people who are not in class, I should. Let's make sure that the polls are there. They're more or less regular. Sometimes I will skip them, sometimes I will have them, but they will judge your participation in the lecture, right? So if you are not answering the poll questions during the lecture, it's your choice, right? So, and you lose this 10% of your grade. And so because I get those emails, okay, can I redo it? I didn't know. Wow, like last poll, everyone gets 100%, but from today, we'll grade them, right? Okay, so that's cool. And if you're in class and suddenly your machine fails, you say, I cannot submit, just come talk to me and I will, I know you're here. I will record on paper, let's put it this way, and then I'll put it in. Okay, so finally back to the lecture. So just a quick reminder, what we were doing. We were trying to look at x86 assembly. It's kind of crucial to understand what the machine instructions are, and assembly is just a human readable way to interpret machine instructions, right? So essentially, the machine instruction is the thing which like goes into the pipeline and drives the execution of the pipeline logic, right? All these logical gates, decode the instruction, like read the registers, execute it, right? We talked about it. And so, but if you want to understand how operating system executes even the simplest programs, you have to understand what's inside them, right? And what's inside them is actually what compiler generated. Compiler generated machine code. We will take a look at real code which compilers generate probably next time. And then we will understand what is that execution environment which is needed to run this code, right? So C has a very minimal runtime. Essentially, it's just a stack, roughly speaking. You don't need anything else. You can execute C after that. But other languages might need a like more involved runtime, but you will understand what's inside if you understand what's inside a simple C program, right? So that's why we're looking at this assembly instructions. So very quickly, and I will go a little faster today because roughly speaking, I want to finish because otherwise we'll get stuck in this. So, but let's try. But again, feel free to interrupt me, right? So just a reminder. So we looked at it. x86 has 8 registers. They have those unusual names. Sometimes the names mean something like a stack, for example, or a base pointer. We'll understand what it is. We have this notation to make sure that we understand what that instruction can operate on a specific operand, right? So, for example, on any general 32-bit register, right? So we started looking at simple instructions like, for example, move, which can move data between, for example, 2 registers. And in Intel assembly, which I'm using in this slide, the direction is the following. Goes like this, right? So essentially, it's a little unusual, right? And like in the other assembly, AT&T, the direction will be different. So literally, it will be reg 1 into reg 2. And this is AT&T. And this is Intel. So again, I will always try to clarify from the context what is going on, right? Because sometimes it's like, if it's not clear, feel free to ask me. I get confused myself, right? Every time I come back, I think, okay, well, which direction? I don't know how it happened that they did it so hard for us, but this is how it is, right? So just a couple of examples, right? So here, instruction move copies the value of the EBX into EAX, right? Every time I look at it, I have to remind myself. Here it stores 5 into a memory location pointed by the var. It's a little bit funky here because what is this var? It looks like a variable, but in assembly, it's just a label which is attached to a specific memory address. So effectively, when you write an assembly program, you say, look, please reserve me a little bit of space, like let's say maybe 1 byte. And I will call this space var, right? Or whatever, like your label. It's kind of like a label. And then you can use this label and the compiler will make sure that instead of this like human readable label, it will put a real address here. And when we get to linking and loading, we'll understand how this compiler toolchain along with the linker and loader will make sure that the address is really where this variable is in memory, because the operating system can move the program a little bit, right? Question?
Yeah, I'm going to ask, how do I know this operation is successful or not?
What do you mean?
I mean, you said you store 5 into PC address.
Mm-hmm.
How do I know?
How can you know?
Yeah.
As
or the guarantee 5 definitely.
Oh, is asking if that can possibly fail?
No, I kind of get it. Yeah. So no, thank you. That's a great question. So it's just that the way you phrase this question is a little unusual, right? So, and I start thinking about it. Like, let's rephrase it in a simple form, like your classmate is saying. So, can it fail? What do you think? Can it fail?
Yeah.
Yeah. Okay. Why?
I have my figures in view.
So no, that's for real. Gamma. So it's physical error. And you can laugh at me, right? But imagine you're running a data center, which, like, let's say 10,000 machines, a typical size, right? The probability of one of those machines failing is reasonable. It may not be a gamma ray here on Earth. There in space, it's a different game, right? Yeah, it happens, right? And so in those data center quality machines, the memories which you buy, they come with error correction codes. The chances of like large memories failing are so high that you pay extra for have like extra bits in the memory to make sure that, you know, you can correct 1 or 2 errors, right? So typically 1, I think, right? So that's one way to fail. So in this point, the answer to your question, if the error correction code can handle it, it will be transparent and the hardware can tolerate the error. It might not be always the case. And then what happens? Do you know?
There's a flag in the CPU that gets raised.
Right. There is a specific exception. I think it's called machine check exception. It's some critical machine error where like the hardware tries to detect an error and says, okay, well, we're failing. So there is no way to make future progress, right? Sometimes the hardware even fails to make this error. And then which creates an opportunity for an interesting attack. So this attack is called the roll hammer. Roll hammer is a line of attacks which uses those physical flows in hardware. So for example, in order to retain a value in memory, the memory itself has to refresh the value every so often, right? Because the value is sitting in a capacitor and it's slowly losing a charge. So if you don't refresh, it flips from 1 to 0, for example, right? Roll hammer is an interesting flavor of attack, which stresses this memory line, draining the charge faster than the hardware refreshes it, causing a flip. You say, well, what can I achieve? There is a kind of like, if later on, if it's a page table and it flips from user accessible, kernel accessible to user accessible, you suddenly allow user to access a page, right? And write memory maybe. But there were like more interesting attacks where people were flipping a character in a router table and making sure the DNS name resolves to a very close DNS name with a 1 character difference. So it's kind of cute. So I'm not an expert on those attacks, but you can see that hardware can fail. And there is like a line of research for how to ensure that those attacks are either impossible or harder to make. Again, go take an architecture class. Rajiv teaches a good one and ask him, okay, or read about roll hammer. So it's a lot of fun. So can you fail in any other way?
The address is invalid.
Invalid address.
Yeah.
And we've seen it, right? So how do we usually see it as users? You get a SAC fault. And later on, I mean, we're all kind of used to the fact, okay, it can SAC fault. What does it even mean, right? Later on, I will explain. But essentially, usually you don't pass a check that you can access this region of memory. So maybe it's not allocated and maybe it's not mapped. Or maybe you don't have access permissions. You're trying to access kernel memory. And what happens is that the translation memory, virtual memory address translation mechanism detects the error, raises an exception, the operating system processes the exception and typically terminates the program, right? And that's why your program exits with a SAC fault. And we will, again, later on understand what's going on at the level of details. Like we will understand what segments are, what the page tables are, and then you will understand how it works, right? But at a high level, this is it, right? So this is how it can fail. And maybe there are some other exotic cases as well, right? But let's assume these are the two most interesting ones, right? Oh, it's a good question, right? Just for the sake of understanding that it can happen. Okay, so let's skip, this is where we actually stopped last time. So normally when you program in C, you have some data structures, right? So like this one, for example, it's a point and it has 2 coordinates, X and Y. Each one is an integer, let's assume it's 4 bytes, right? So in memory, it will be something like this, right? So we'll be sitting X, sorry, that's my X. and this will be sitting Y, right, in memory, right? And imagine if you have array of 128 of those, right? So you have real array of 128 different points, right? So like this. And inside each point, you will have X and Y. Sorry for like handwriting is not ideal. Just rewrite X and Y, right? So normally in C, you do something like this. That's your code. You say, give me the ith element of this array, and specifically give me the value of Y, right? So, okay, x86 back in the days decided, okay, it's so common to have this pattern in your code that we will have instruction support for it, right? And they allow you to compute this address immediately within the same move instruction. So they say, okay, look, EBX is the beginning of the array. So it points to here. EAX is an index, I, right? Since each element is 8, we will allow you to multiply this index by 8, right? And we will allow a small offset +4 to get from the beginning of the element to actually element Y, field Y, right? So that's possible in x86 as well. And you will see those instructions. Typically, those are patterns of where you access those data structures. So this is clear, this example, right? Okay. There's a second instruction, which is less usual, because move instruction takes this value of Y from memory and puts it into the register, right? And LEA, which stands for load effective address, instead of loading this value, just gives you the address of this. So there's a long text here, but let me just illustrate with an example. It's a little bit simpler. So if here we just say we want a value of Y, right? Whatever it is, 5 maybe. Here we just say, give me an address of Y, and I would assign it to a pointer P. And so for that, you use LEA, although like they are almost identical here, right? Because you say, look, it's the same thing. It's the base of the array inside EBX. It's the index I inside EAX and +4. But here, instead of loading the value, you're just loading the address. So if we have memory like this, right? This array, this is the point which we're looking at, point, ith point. So, and here two value, 5 and 7. So move will load 7 into the EDX, and LEA will load this address, whatever it is. Let's say X5005, right? So ESI will get this OX5005. Clear? So this is, you will see those LEA when compilers do use them when they generate code. Okay, so that's reasonably easy. LEA is often, it's often abused as well. So it's, again, there was an intended meaning for this instruction, but you will see that compilers use it in a way when they use it as an arithmetic operation, because LEA can perform those funky additions. So for example, it can add either 2 or even 3 operands, which sometimes is useful. It can also store in any register, not in the source register, because later on we will see that if you do something like add EAX EBX, so the result of this addition is stored in the EAX. So EAX get the value of EAX plus EBX, right? And it's a little, sometimes it constrains how you can generate the code, right? Because, for example, in this case, you're losing this old value because it gets overwritten, right? And in case of LEA, you say, look, I'll save it because I will be reusing this value in the next 5 instructions, for example. So let's save it in some other register, right? And it also has this funky multiplications by a limited set of constants, right? So like by 2, by 3. So just like, again, if you see it, it's not always the address of a field. Sometimes it's also just abused by the compiler. So don't get confused about it. What is that? Well, yeah. Okay, so we got the memory, we got the move instruction. So allows us to move from memory to register or between registers. Now we want to do some arithmetic on that, right? So not surprising. So those instructions look something like that. So for example, addition. Again, syntax can add two registers, can fetch a value from memory into a register, or can fetch a value from register and save it into a memory after adding, right? Can add a constant and can add a constant to memory, right? One thing which I wanted to emphasize is, if you were careful enough, and probably you were not because I didn't say that, so it didn't, like, none of this instruction has anything like two memory operands, right? So move didn't have it. So if you carefully look, I mean, I myself, I didn't notice it immediately when I first looked at the x86 instruction set 20 years ago or 25, I don't know when. It just comes to you when you start typing code and you say, oh, let me just do that from memory to memory while it doesn't compile. So again, that's the limitation. So it allows you to use memory as one operand, but not two. So you have to put in the intermediate register, right? Good. Okay, cool. But still, yeah. And encoding, as I said, a little bit limited. So you say, look, I can add a constant to a register and put the value back into register, right? So here we're adding 10 to EAX and putting back in the EAX. Here we're adding 10 to the constant, which is actually a single byte constant, stored in memory at address var, right? But again, the point which I wanted to make sure that if you have a register here, you will lose the old value. It gets overwritten. But otherwise, fine. So subtraction, similar deal. Essentially, you have two values here. And you're subtracting one from another, saving the result into this one, right? So here we, for example, subtracting 216 from the value stored in EAX, right? They have specific increment and decrement instructions, which increment and decrement value by one. So similar deal, but takes only one operand. So just increment or decrement in this example of EAX. Here we're incrementing memory location pointed by var, right? They have bit operations, logical and or XOR. So again, here is a good example. So it clears all but the last 4 bits of EAX. Does anyone know why it works that way? Okay, first question. Yeah.
Oh, I was going to ask. So this one it said
Wow. I guess it also depends on 32-bit versus 64-bit. I think, yeah, on 64 bits, the word will be, I think, 64 bits, if I remember correctly. On 32, I'm guessing from the slides, and I don't remember like exactly, but I'm just trusting the slides that yes, the word is 32. Right. So, and in most cases, you don't need anything like that, and just the assembler derives the size of the operand from the operand itself. So it's from the value of the register. And I don't exactly remember the rules, whether it can say, by the way, I know the size of var. I'm pretty sure it can, but maybe not. So, and sometimes it's ambiguous, because if you say this memory location as, I don't exactly remember, but let's assume it can. In many cases, it can, because you very rarely see those things in the assembly. But I wanted to ask you this question. So how come it works that we clear all but the last 4 bits of EAX? You can tell me why it works. Because what? Ending it with 4 ones. Exactly. So remember how AND works. So if you have 2 bits set to 1, AND gives you 1. if one of those bits is like, sorry, if your bits are either 0 or 1 and you ending with 0, you always will get 0, right? And so which means that this one is a value f in hex, which is if you write it as bits will be something like, not something like, but exactly 4 ones, right? So these 4 last bits are set. So whatever you have inside EAX, so some bits of 0, 1, 1, 0, 0, 1, 1, and the last 4 bits 1, 0, 1, 0, for example, you ending them with all zeros, right? This is all zeros, besides the last 4 bits, right? So which means that no matter what you have here, like in this part of the EAX, the result will be all zeros, right? And those, it's like a mask, will stay the same because it will preserve their value. You agree? So you probably are familiar with bit operations. Like, I bet that since you're preparing for job interviews, you know them even better than I am. But the simple ones we will see later in class, because when you do some operation on a page table entry and you want to set a specific flag, it's 1 bit. You will see that, okay, we will mask it with just 1 bit, right? Making sure that we're operating on this bit, for example. So similar, if I do this, this clears all the bits of EDX. So why is that? Do we remember how XOR works? Correct, right? So essentially, XOR, if the bits are the same, will produce zeros, right? And so since you're XORing with the same bits of EDX, so whatever you have there, either 0 or 1, you're XORing with yourself, so you will get 0, right? And that's like, again, this trick was used as a fast way of zeroing a register. Arguably on some architectures, and it changes over time. On some architectures, maybe writing a constant 0 into a register was either slower or required an instruction which takes more space. Maybe instead of 1 byte or 2 bytes, it takes 2 bytes or 3 bytes, right? Because it has a constant 0, right? And so XOR saves you either space or time in some ways, right? And again, like, it's not as important. And what I wanted to show you here, and for that I probably have to stop sharing for a second, is an interesting document. Let me quit and show. There is this. Let's go. Let's go. So it's actually accessible from our class website. So let's go here for a second, and I will show you where to look. So here we have additional resources, and we have a couple. So we have those assembly guides, which at least I recommend you to open, right? We also have this operating system from 0 to 1. And in this homework, which I just assigned, I ask you to read a chapter from this book. It's a book on GitHub, but it's a reasonable resource for how to use GDB. It's a reasonable resource for different things, but sometimes it gets a little lengthy. But for how to use the GDB, it's a good resource, right? So please, like, again, I never introduced this page, but take a look. So some of these things are interesting. And what I wanted to introduce, right, like relevant to what we're doing here, there's this guy, Agner Fogh. He's a professor at this Technical University of Denmark. And what he does for each Intel and AMD architecture, at least like as of a couple of years ago, he measures the latencies of individual instructions. So he will tell you how many cycles it takes to execute an instruction. So for example, we say, which one is your favorite architecture? Let's say Ice Lake is probably one of the newest, right? And he says, okay, look, move instruction, when it operates on two registers, register and register here, right? It will take 1 cycle. Wow, that's kind of not surprising, right? If I ask you, okay, how long it will take to read something from memory? So who knows the answer? Like imagine it has, I mean, yeah, my camera is, let's fix the camera first. If I ask you how long it takes to read from memory, so one of these operands should be memory, right? Right, so you quickly look it up and you say, wow, it says 3 cycles here, like a slightly smaller register, or like this one takes 2 cycles here.
Data for the R8.
Ask again, sorry.
Why there's no data for register A16?
Well, not sure. So we can like those tables are a little bit involved, but okay. Okay, it seems that this table implies that reading from memory takes only 3 cycles. I'll ask you a question, why? Prefetching in a cache. Agree, because remember, in all my figures, I draw this diagram where the CPU sits here, memory is somewhere. It's on one slide, but there is a bus in between them, right? This bus is reasonably slow. So how long it usually takes to really read a value from memory? How many? 100 to 400 cycles. I agree with that. So if we, by the way, that's a good exercise as well. And I wanted to kind of get to it. No, okay, let's get to it later. So, right, so I agree. On a modern machine, like the 2 gigahertz CPU, which is pretty typical, right? The memory latency will be roughly 200 to 250 cycles, right? So it's quite a bit of time. But he, in his table, measures the latency of a prefetched piece of data. So because typically, in most cases, when you run your program, the way the memory subsystem is designed, and maybe you will apply those optimizations by hand, you will prefetch the data. So waiting for 200 cycles is a lot, because every 5th instruction is a memory access, right? Either load or store. If you get the stats from most programs, you will get this number. So it means that if every 5th instruction is 200 cycles, that doesn't fly too far. So a CPU has a complicated hierarchy of caches, and essentially the data, if you're lucky, gets prefetched in those caches, and the closest cache to the CPU on this architecture turns to be 3 cycles away, right? So again, it's useful when you design your programs. You can say, okay, well, remember this, we're accessing this point with X and Y in memory. How long it will take me to read Y? Well, this table will give you an answer. So it's like 3 cycles, right? Let's take a look at some other instructions real quick. So addition, for example, we're lucky, like 1 cycle. So we're less lucky with multiplication, right? Because multiplication is a more complicated instruction. It takes a little longer here, right? So 3, 4 cycles, but still not horrible, right? Division is becoming a horrible instruction, right? But again, so as someone who designs low-level systems code, you have to think about performance, right? And this is one way to think about it. So if someone asks you on a job interview and during the class is, here is the piece of C code, it's not even assembly, how long it will take to execute it? You have to eyeball it. You have to understand what memory accesses are or will be in this code, like whether they will be prefetched. If not, then just eyeball by roughly knowing the instruction latencies from this Agner Forbes manual. So it's very useful. And you will see the skill of optimizing to the last instruction is a very useful skill. It will pay you back later in professional life. Any questions? All good? Okay, so just accessible from the main class webpage, right? Okay, let's get back to this slide deck. Play from current slide. Okay, so shift left, shift right. Again, typically in most cases, those shift left, shift right will be used to extract specific bits of a word. So for example, again, if we will be accessing the entry in a hash table and we said, okay, look, by the way, we want to set those ones to some values. We'll typically first create the value in the lowest bits and then shift them to make sure that we will get them here, right? This is what you will see. But sometimes this shift left is also used as a multiplication by 2, because shift left by 1, since that's how you encode the number, right? Like it's a sum of powers of 2. So effectively, it gives you a multiplication by 2 very fast. Because remember, in the Egner-Forbes table, multiplication was roughly 3 to 4 cycles. Division was worse, right? Because division was like 19 cycles. And so if you're dividing by 2, you can obviously do shift right, and it's 1 cycle, which means that if you're designing something like a data structure, like a hash table, and you want to do a modular operation, kind of like saying, okay, does it fit or wraps around? Better have it with a power of 2, right? Because it will save you those 19 cycles. And that's a lot if you like do a lot of memory, like hash table accesses, right? Is this argument clear? That sometimes it's useful. Okay, but not surprising. So if you like, again, that roughly, if you remember C, you will, well, there's addition, there is subtraction, there is those bit operations and shift lefts and rights, right? So they are in assembly as well. Like I already mentioned, there is multiplication. So again, to like multiplies the content of EAX by the value inside the var, pointed by the var variable. And it takes a while. There is this different format. So essentially multiplies EDI by 25 and puts the result back into the ESI. Like division has a similar format. You will never see a division in this class. I don't even think you will ever see even multiplication. As systems designers, we will be super careful. Everything will be a shift, multiplication by 2 or division by the powers of 2. Never by any other number. There is a not a negation, right? So negation, for example, puts like takes a negative EAX, reverse the sign, puts it back in the EAX. So again, it's not super complicated. So this core set, you can just easily look it up on like on any, like, again, just let me stop this slideshow first for a second. I just wanted to get back to hold on here. Where's my here? So I wanted to get back to the class page and make sure that we have this too, right? So this is the guide which we're using, and you quickly can look up the instructions which are covering in this lecture will be like here, and essentially my lecture follows this manual. If you need more help, you can go into get a book like freely available. So for example, it will tell you like how to essentially like write an assembly program. Like there will be deeper explanations of all instructions, but for the purposes of our class, you can have this high level understanding of what's going on, and it's easy to guess from the name of the instruction and stuff like that, right? And if you really want to understand, okay, move instruction Intel, you can look it up online, and there will be something like one of those websites which really provide you like real set of all operands which you can provide, and will provide a pseudocode for this instruction, like with all the checks and everything, right? So if you really are worried about that, and it sometimes happens, you know, like you have an exception and you think, okay, but I'm accessing this address which should be mapped, and then you see like look up this pseudocode which comes from the Intel manual, and you can understand that, possibly can understand what the error is, right? Just wanted to make sure that we understand this as well. Okay, so back to the slide deck. Whatever I covered here is basically enough to do any arithmetic, right? So essentially you can write programs. Well, not really any, but if I ask you what is missing, which programs you will not be able to write with the instructions which I introduced? Anything with floating point. HCI people are like, yeah, we really need them. Like systems people. In this class, you will never see a floating point. You're right. Or extended register. Any other ideas? Like something is really critical missing here. Exactly. So anything with a loop or if then else is missing. You will be surprised. I mean, like I like those stories, and maybe I should introduce them maybe next time. But there is a way to write programs without if then else statements. They relied on those conditional instructions, meaning that x86 has this extension which allows you to say this move either happens or not, depending on the value of the flag. And you can rewrite your code in such a manner that you use those conditional move instructions. And essentially, there is like you say, for example, my team will build a database, like an SQL server, which has no loops or if then else statements. Besides the jump backs, like essentially large fors, which are publicly, the lengths of which is publicly known. Why is that? Because there are attacks which allow you to extract the data set by monitoring execution of the if then else statements, because it turns out that it's another side channel and there's a way to collect which way the branch went. And for example, if there is a branch which says if A equals to 1, then do this. And you obviously know that A was 1 at this point, right? So if you're talking about RSA keys, you can learn bits of the key, for example, right? So, and those conditional instructions allow you to build those programs which essentially hide those patterns. Again, so it's possible to go without jumps, but really you probably want to jump back. Okay, but before we do this, let's try our game of the poll, right? So essentially, are you guys? Does everyone have a poll everywhere account, which is set up according to those rules of like UID, like the email which you have to enter is U0 or U10 and U105 and so on with an @ sign, because that's how I will use my Python.
The slide show is about, yeah,
Let me just fix everything. No, okay. So why is that? So why am I asking a question on a slide versus asking it in poll everywhere directly? Or maybe I'm already asking it directly. The problem is that no, because I really cannot put this code on the poll everywhere, right? So it doesn't have a markdown support. So essentially, what I have to do is if I want this like really well structured question with an instruction, initial values and stuff like that, then I really have to like ask it separately, right? So let me go and fix the on poll everywhere. Just a sec. And so you guys are already seeing the poll. So it's active actually. Ah, man, interesting. I was thinking that it only gets active when I actually get to that slide. Oh, it's been active the whole lecture, but only this question for all of them. Yep. Only this question. So I'm asking what's inside EBX. Yeah, I should be probably asking what's inside. No, what's inside EBX, right? No, it's Intel. Sorry. Wow. But it's okay. So and that's fine, you know, like that's why we're doing it. My impression was that the poll should be only active when I'm where's my slide deck? Man, it's so hard to get the slide deck. I will close this one. Minimize this. Man. I see my skiing videos. I see everything on my screen. Got it. Maybe towards the end of the class, I will learn how to use macOS. If I will be able to survive. So right now, my problem, I actually cannot find my slide deck. Can you believe it? Where is my slide deck? Just let me figure it out. Okay, put your answer for now, and we'll discuss it quickly. That should be my slide deck here. Oh yeah, I found it. So I thought that this is only when I switch to this slide, it becomes active. The other funny part is that on my screen, it doesn't show the answer slide, but here it does. Okay, everyone filled in the poll? Everyone participated? So let's, okay, that's the disadvantage of this system, right? Because I should probably try to at least repeat the question here, right? Because there is a certain disconnect. But if I show you this slide and the question there, and hopefully I didn't get confused about what I'm asking, the answer should be clear, because and from here it's more clear. So on Intel assembly, right? So we're moving EAX into EVX, right? That's what I wanted to emphasize on this silly question, the direction of the move, right? And so if EAX contained 2, then after we moved 2 into the EVX will contain 2. Agree? So that's what we. Again, feel free to fix the answer to make sure that I think I allow multiple submissions, and I mean, the grading scheme, which I adopted from none of the above. Good. Okay, who has answer none of the above? Okay, someone who is. Well, can it crash? Again, I don't think there is a way for this instruction to crash. Move. And again, you will see in this pseudocode, which I was showing just a second ago from Intel, right? There will be exception conditions for many instructions. For example, for division by 0 will cause an exception. Move of 2 registers shall not crash. You only have like a critical machine error where, you know, the pipeline, at this point, you probably will not even get an error, right? Okay, good. So everyone is correct. So I wanted to say that the grading scheme here, favors participation. So even if you leave a wrong answer, I'll give you like at least half of the grade, right? But better get the right answer. Okay, next question. So what is this instruction doing? Is it reading memory or writing memory?
It's still on the last.
Ah, man. Yeah, sorry. Like, integration was supposed to be a little better, to be honest. And I cannot. So what if I click here? Like now it switched, right? So let me go back. Reading memory or writing memory? Reading. So everyone agrees on this, that it's reading memory? Yes. Yeah. Okay, easy. And I'm surprised that poll everywhere actually works that well, to be honest. I mean, kind of well. It's a lot of fun, but again. Okay, my last question. Is this a legal instruction? Let me just. No, why? Who can tell me why?
No two operations on the memory.
Right, because here we are essentially trying to get a value from the memory location pointed by the EAX register and put it into the memory location pointed by the EVX register. And we just discussed that Intel assembly doesn't like it, right? Okay, good. Everyone participated. So, okay. And now we go to a more interesting part, right? So control flow instructions. The first couple will be relatively simple. Again, what is this control flow, right? So we mentioned it before. There is a special register, instruction pointer, which points to the current location in memory, which CPU will, from which CPU will fetch an instruction and will try to execute it, right? Again, we kind of understand that it can actually fail here, right? So for example, even the read of this instruction might fail, right? Because maybe instruction pointer points somewhere where memory is not mapped, right? So you can't even read instruction. You will get a SAC fault, right? Or maybe you will, while executing this instruction, you will encounter some kind of a segmentation error or memory error, right? Or division by zero. Okay, one interesting part about instruction pointer that it cannot be changed directly. So you cannot do a move into an instruction pointer, right? Because it's supposedly it's not part of the general register set, right? So it's a separate register. However, you can change it with a specific instructions like jumps, call, stuff like that, and returns, right? So normally it will just simply increments to the next instruction in memory, right? And that's the logical flow of how CPU runs. But it can be updated, right? And with those control flow instructions. So, for example, let me first introduce the idea of labels. So the assembly allows you to mark a position in your program with a label. So the label is just a piece of text with this colon symbol, right? And then you can use this label later to jump or redirect instruction pointer to this label. So for example, an unconditional jump, it just jumps no matter what. So if you have an instruction which is like this, jump to a label, the control flow will go to that position in the code, right? So for example, jump to begin, well, the next instruction after this jump will be this one, right? Non-conditional jump. So again, labels are just human readable marks, right? So, but assembler itself will make sure that when it generates this instruction, it will really put like an opcode and the address where you're jumping. And the way these instructions might be encoded is that it's actually not an absolute address, but a relative to the current address, right? So it can say jump plus 5 instructions or 5 bytes in memory, or jump -5 and you jump backwards, right? Okay, that's nice. Of course, again, like you can maybe write my funky databases with a non-conditional jump, but let's not better do that. So typically you need a jump which either happens or not, right? And on MIPS, which you probably covered in your architecture class, the condition will be in a explicit register, which you provide as an argument to the jump instruction. On x86, it's a little bit less obvious. x86 has a specific register. It's called E flags. No, normally it's called the flags register, but E stands for the 32-bit version of this register, right? On 64-bit machines, it will be R flags, right? And this flags register reflects the information about previous or the most, previous arithmetic operations. So for example, flag 6 here indicates, or bit 6, sorry, in the E flags register indicates that the last result was 0, for example. Bit 7 indicates the last result was negative, right? And based on this values of those bits in the E flags register, those jump instructions will either perform a jump or not. So for example, jump 0 jumps only to a label, only if the last, like if this 0-bit set is set, right? So what you do instead is that like typically a little small. So you have all possible combinations like jump when equal, jump when not equal, jump when 0, jump when greater, jump when greater or equal, jump when less, jump when less or equal. And typically you invoke one of those arithmetic operations CPU has a specific like designated compare instruction, which compares EAX and EBX. And if comparison is true, like essentially you jump based on this condition. So you say, here I will be jumping only when it's less than equal, right? And internally comparison is just a subtraction, right? So which sometimes confuses you, but in most cases don't. No, it's a combination of bits. So because the flag will contain the minimal set of bits which allows you to derive this condition, right? So for example, less than means that if you do a subtraction, the result will be negative, right? And then based on a negative flag, you jump or not. It gets sometimes confusing, even for me, like, because, you know, it's not you who write this code, it's typically a compiler. And sometimes the way they encode those conditions might be like slightly odd, but in most cases, you can figure it out. But I mean, I've been confused myself. Any other questions? Good. Okay, so we got it. So comparison essentially, just to make sure that we understand how it works, like just compares the two specified operands and sets the condition in the E flags, right? So, and again, a typical set of possible combinations of memory and registers, right? So for example, here, if the 4 bytes stored at the location var here are equal to the 4-byte integer constant 10, so the jump will go to the location label loop. So jump when equal, right? So internally it comparison performs a subtraction, result will be 0, so means they are equal, and that's how it will work. And it will jump when equal to the loop label, right? Okay, that's fine. That was relatively easy, so not super hard. You jump loop. So by the way, do we understand that those jumps allow us to encode, or not us, but the compiler to encode things like loops, right? For I starts from 0, I less than n, I plus plus, right? A typical thing will be something like a loop label. And somewhere here, you will jump. Like, depending on how you encode this loop, you can set I initially to 0 and then subtract. And then you will jump when probably you will jump not 0 back to the loop, right? Or you can encode inequality and then will be jump when equal, right? Back, oh, sorry, jump when not equal to the loop, right? And then you have the body of the loop here, and the loop executes multiple times before you essentially the exit condition is true or the jump condition is false, and you start executing those instructions, right? That's clear? Just wanted to make sure how compiler encoded. And I promise we will take a look at the examples of real code like C, which would compile into assembly, and we'll take a look at how it works. But another thing which I wanted to make sure that we understand is that those also allow you to encode if A equals to 0, then and else something else, right? So how will we encode this? Let's say CMP, let's say EAX, which contains A with 0, and then what?
Jumping or equal, not label.
Yeah, or you can actually jump when equal as well. It just depends on how you want to order then and else. So if they equal, you jump to then, right? And you will have the then label here, and instructions from the then part of the statement will be here. And here, you will have instructions from the else part. But what you need here is just, you need an unconditional jump. Like, I don't know, let's say end. And you will jump here where the code merges, right? Is this clear?
Yes.
And you will see, like, in compilers do different choices. Like, you will see where loops are compiled differently, even depending on the version of the compiler, of the same compiler, or depending like certain flags, which like even sometimes the language runtime specifies, right? So, but in most cases, it's possible to figure out what's going on. And it's also like the beauty of those languages like C and Rust is that you can actually read the assembly code and still understand what's going on. In C, it's super easy. In Rust, depends on the Rust code which you're like looking at. So depending on the layers of language abstractions, like option types and stuff like that. If you don't have them, it's almost like C, then you will just see the same assembly, which is pretty cool, to be honest. Okay, so we understood the control flow. So we understand that if then else and for loops and everything is there. Now our goal is to understand invocation of functions or procedure calls. So like if I ask you a question, why do we need procedure calls to begin with? Trivial question. No one, everyone is shy. Let's pick a person who never said anything. We have this volunteer. No, okay. But anyone who wants to say. So why? Tell me. Correct. Right. So what you're saying is that functions allow us to hide implementation behind a contract, right? In a language like C, the contract is typically just in a function name. So for example, it will say read a file, and you believe that if you provide the specific arguments, it will really read a file. And inside it can be whatever. Maybe it just invokes system calls or goes to some kind of a caching subsystem where this file is already cached, right? So you don't know. But for you, it doesn't matter. You just always read a file, right? So it allows you to hide complexity. What are the other reasons? There is one more. Correct. Correct. And so you can also reuse the code. And more interestingly, you can build those recursion, right? So you essentially say, well, it's easier to write this code in a recursive manner, invoke the same function twice, maybe, right? Or 3 times or something, right? And despite the fact that we are usually say, okay, don't do recursion because there are some like overheads of doing that, it's still a valid argument. Or like even you can invoke it from multiple times or from multiple spots. In order to implement a function invocation and specifically support this idea of recursion, C relies on the idea of a stack. So what is this stack? There is yet another register, right? And I mean, not surprisingly, you can guess that what it is. It's this stack pointer register, which contains an address, like I can say points to memory. And this area in memory, like notice that it's like 0 here, max address, which is in this like 4 GBs all once in the 32-bit machine, right? So it's 4 GBs. It actually kind of like, I will use the word grows, but essentially you point to the top of the stack, right? And essentially the data which you'll be saving will be here on the stack. So the stack is not this way, but the other way. That's what I wanted to make sure we understand, right? Okay, so what is the role of this register? Who knows? Who knows what stack is already?
Of the stack is.
It keeps track of where the top of the stack is, but semantically, what will happen to the stack when we do something? And what is this something? A little confusing, so maybe a more cleaner explanation.
As you
Correct. So I agree with you. So again, just let me say it here, but then later it will become clear. The primary reason for this stack is to remember the address where you have to return when the function is done. meaning that it might be not trivial. I will show you. If you invoke a function from two different points in a program, how do you know when you reach the end of the function whether you have to return to one point or to another, right? You put this value on a stack, the return value, and then the return instruction will read it from the stack and will return to that specific location. And the secondary main purpose is to provide allocation for local variables. I will explain what these are, but you can intuitively feel that if I invoke the same function recursively, right? And if there is a variable a inside the function, in one invocation of f, a might be equal to 1, in another it might be equal to 2. And we need to have memory where to store this information, right? Okay, I'll explain it, but just keep that in mind. Okay, so again, a couple of rules here. Stack is nothing super special, right? Because sometimes if you're doing like a compiler or language level class, you might think that stack is a little special. In systems class, stack is whatever the ESP points to. So as an operating system designer, you're free to change the ESP, like essentially assign it a different value. And if this memory is mapped, well, let's see what will happen. So typically, this all is hidden from you, but like some funky language runtimes, like asynchronous runtimes in C and Rust might play those games, right? Or green threads and like in C will play those games, right? And they're hidden from you. But as a systems designer in this class, you will see that we will set the stack to whatever we want, right? And sometimes we will change it, right? Well, that's fine. Again, like let's just illustrate the 2 points which I was trying to make. So like as I was saying, functions can be called from different locations, right? So sorry, I broke the slide here. So this is location A, and this is location B, right? And when you execute this function, again, inside foo, when you reach the end of foo, you need to know where to return. Are they either to the next instruction after A or to the next instruction after B, right? And so this information you will save on a stack. So let's take a look how it works. So for example, this is a diagram in which I say, look, you have your next instruction you're going to execute is this call instruction. Call instruction is an assembly instruction which changes the instruction pointer to the label foo, but it does something else additionally, right? What happens first is that we actually, when you execute the instruction call, it takes this address of this next instruction and puts it on a stack. It just internally computes the current value of the instruction pointer plus the size of the call instruction, because call instruction on x86 can be different size, unfortunately. On MIPS, it will be just plus 4 bytes, right? So not hard, right? Or on 32-bit MIPS, right? But here we say, look, the CPU follows this logic, computes the size of this call instruction and says, okay, this is the next instruction, this address A, and it pushes this A here on the stack. And then redirects the instruction pointer to beginning of foo. So first it actually will adjust the instruction pointer to make sure that if you do something with a stack, the next value will be written here, will not override this old value of which you saved on a stack, right? And you saved 4 bytes because it's a pointer. And then you adjust the value of instruction pointer to point to the foo label, right? And at this point, you start executing foo, right? You execute the first instruction of foo, you go forward, right? And at some point, you're reaching the end of the function. And there is a special instruction, which is called RET, stands for return, which specifically tries to restore the control flow, like essentially restore the value of the EIP to point to this instruction, right? Because this is where you originally called foo from, right? And this address A, remember that it's sitting on a stack here. And what it does essentially, it specifically reads this value from the stack and sets the EIP to this value, and obviously adjusts the stack saying, by the way, like this piece of information is no longer relevant, right? By the way, this A is still on the stack. It's not like deleted. It's not overwritten with zeros. It's still there. It's just that logically, the next attempt to call something will overwrite it with a new value, right? So because this is your current stack memory. So this stack is a kind of like a tiny memory allocator, which says, okay, this is the free memory, and everything what is like above, because it grows towards 0, right? Everything what is above was probably used in the past and may be useful in the future. We're not going to touch it, right? But this area of green current stack area is fine to use, right? So did you get this, how it works, the instruction, the function invocation, right? So reasonably easy. And you see that it actually supports recursion, because if foo internally calls itself, well, something else will be saved on the stack and something else, right? And you can invoke foo multiple times and then return multiple times. You might fail because maybe you might run out of stack space, right? It can happen, and you've seen it in your programs. So, you know, that's why we say, wow, be careful with recursion. Don't allocate a lot of local variables, because you will run out of stack space faster. And the reading system, which starts the program, will decide the size of the stack. Typically, it's just a constant. On x86, it will be just 1 page of memory, so 4096 bytes. On Linux, it's probably like by default maybe 64 kilobytes, something like that. But it might vary from the language runtime and stuff like that, right? Okay, so again, just to reiterate my explanation of the call and return. Call semantically internally pushes. I didn't explain what pushes. Let me explain in a second. Pushes the EAP on a stack, and pushes the EAP plus the size of the current call instruction on the save on the stack, and jumps to the label provided inside the as part of the call instruction. And return essentially pops the value from the stack and jumps to that address, right? So let me quickly introduce what these push and pops are. So first of all, so here I again just trying to briefly enumerate the other uses of the stack, and we will cover them on Tuesday next week, right? So it also a couple of them. So it provides storage for local variables, right? So if inside foo you have a version of this int a, this space for int a will be allocated on a stack. How will it be done? When you save the return value here as part of the call instruction, the very first instruction here inside the foo will say, by the way, adjust the stack pointer to make sure that we reserve some space for a, right? And again, I will cover this next time in details, how these calling conventions work and stuff like that. But also, sometimes you pass arguments on the stack, because we're going to talk about calling conventions. And the question is when you invoke a function like foo and you pass a bunch of arguments, a, 5, b, c, the question like where these values will be stored. Some of them can go into registers, but sometimes you will run out of registers, and then you will put the other like 5 extra arguments on the stack, for example, right? And the function foo itself will read them from the stack. Sometimes you just run out of registers. Remember I said this addition, EAX, EBX overrides EAX. What if you want the old value of EAX? You will save it on the stack temporarily and then fetch the old value back, right? And it's done with this 2 instructions. So very simple, push and pop. So if you have a push instruction, so here is your stack pointer points to the stack, you execute the push instruction, which pushes the constant bar on the stack. What happens is the following. Let's click again. So essentially the value of bar is pushed on the stack, ESP is adjusted to reflect the fact that this space on the stack is already taken, right? So here, if we're pushing an integer, we will subtract 4 bytes from the stack. Remember, stack grows towards 0 addresses. And similar pop instruction does the opposite. So you say, well, pop EAX. So whatever is saved there on the stack, this value bar will be restored in EAX, right? And this, again, the stack pointer will be adjusted to reflect the fact that this memory is now free, or the old value of bar is still sitting there physically in memory, right? So, okay, I'm lucky. I made it till the end of this lecture, which is good because we can start a new lecture next time. Any questions about instruction set? We probably have maybe a minute, maybe less.
The size of the stack.
What is what?
What's the size limitation of the stack?
Set by the operating system. So you can make it as large as you want, but typically people pick a meaningful value like 64 kilobytes on Linux, 4 kilobytes on x86. Okay, thank you. So I'll see you then next week. Don't forget the quiz will be assigned on, let's say, Friday night.
Thank you, Professor.
Yeah.
On the full VE thing, I only got 2 of the questions showed up for me.